Sorry, so my student gave another talk in another room, so another talk just finished, I come back later, sorry. This one.
Okay, so apparently it's very busy. The next speaker is Guoliang from Tsinghua University, talking about overlaps and similarity with theoretical learning.
Good afternoon. So I would like to introduce our work, overlap set similarity, and this collaboration work with my former student Dongdeng and Professor Yu Feitao from the Chinese University of Hong Kong. So the overlap set similarity has many real applications. For example, in Facebook, we want to do friend recommendation. So we want to find all the pairs of users who share at least 3 common friends. In this way, we can do the friend recommendation. In Amazon, we want to do the product recommendation. We want to find all the pairs of items that share at least 3 transactions. In this way, we can do the product recommendations. So there are some applications. Next, I will formalize the problem. And given a collection of size and constant inputs, and we want to find all the pairs of the size that share at least 3 common items. So here is an example. And we suppose we have 5 sets, and each set could be a bag of words or a set of users or other data. In this way, we want to find, for example, suppose the threshold is 2, and we want to find the pair of the size that share at least 2 common elements. For example, in this talk example, we have 3 results. R1 and 2 share 2 common elements. So this is the problem. And the next challenge. For example, in Facebook, there are 1 billion of users. And all existing algorithm has quadratic complexity. For example, suppose we have 1 million sites. The complexity is 1 trillion. Suppose we have 1 billion users. All the work is very, very expensive to do the joint problem. So in this work, we propose the first sub-quadratic methods. So I just show the basic idea, and we split the size into 2 parts based on the size of the size. And we handle the 2 sizes separately and devise different algorithms. For example, here, suppose we have size boundary x. And we split the 5 sizes into 2 parts. The first 3 sizes has less than 5 elements. And the other 2 sizes has more than 5 elements. In this way, we can divide into 2 parts. And for the small size, and we devise algorithm, we want to find all the results between the small pair, small size. And for the large size, we devise algorithm to conduct a Hansen product between the large size and all size. In this way, we can handle this joint problem. For the small size, we use enumeration-based method. For each set, we generate 3 subsets of the set. For example, for R, we generate all the two-size subsets. And for R2, we also generate the 2-size subsets. In this way, for each set, we generate 3-size subsets. And then 2 sets is an answer if they share at least 1 common 3-size subset. In this way, we can just first generate all 3-size subsets and build an index. And the inventory list, all the pairs in the inventory list are answer. So we can handle the small size. Next, for the large size, we just use a very naive method. We first build a hash table for the large size. And then we scan each set. And we probe the hash table of the large size, and to check whether each set has more than 3 common elements with the large size. So this is to process the large size. Then, because we divide size based on size of the size. So just each size of the smaller size is smaller than x. So the number of large size must be smaller than n over x. Because if the number of large size is larger than this number, then the total number of size will be larger than n, where n is the total size of all size. So we can say that okay, the complexity of the large size is n squared over x, because the size is n over x, and we just need to enumerate all the size, and there's another n, so the complexity is n squared over x. And for the smaller size, okay, for the smaller size, we just need to enumerate all the C subsets. So, for example, the size is x, so the complexity is xc. But we know that the sum of all the x is at least n, so the complexity is xc minus 1 n. And next, we need to enumerate the inverse list. So, suppose the number of results is k, so the longest inverse list is at most the square root of k. So the complexity is for the small size. So we want you to achieve the best complexity. We just let these two numbers equal, we can deduce the complexity. So the complexity is subquadratic. So this is the first contribution. We propose the first subquadratic algorithm. So next one, how to select the size boundary x. So we know that with the increase of x, the large size, the complexity is decreased because there's smaller number of large size. And the complexity of small size will increase. In this way, we can just find this point to achieve the best performance. So we can using the choose the algorithm to select x. We can also use a sample to select x. For example, with the increase of x, the benefit is the time of the large size is decreased. The cost that is the time of the small size is increased. So we just increase x and find that the benefit is smaller than cost, then we can stop. Then we can select the good x. So the second contribution, how to select the best x for the set boundary. So next one is that some people may doubt that if the size is very large, how can you to enumerate all the C size subsets? So we propose two techniques to avoid enumerating all the C size subsets. So we use a heap-based methods, and here I only introduce two observations. The first one is that, for example, each column is a C subset, and each row is a set. So this is inverse list, and we can say that if the inverse list has only one element, then we do not need to enumerate such C subset because they can't produce any answer. The second observation is that if this inverse list includes or is subset of another inverse list, we do not enumerate this C subset because they are contained in this inverse list. All the answer will duplicate. We can avoid such C subsets. And for more details, you can refer to our paper. Okay, only 1 minute. And so we try 4 datasets and with different size distributions. And this figure shows that with the increase of x, the cost, the time, is first decrease and then increase. So we must select the best size boundary. And we have 3 methods. The first one is by complexity, by all methods, and the best. We can say that all methods nearly achieved the best performance as good as the optimal one. The next one is, can all methods achieve subquadratic? So in the x, this one is 1 million, this 3 million, so the size is 3 times. So if the performance is less than 9 times, then it's subquadratic. So we can say that this is all methods only increase 5 times, and all existing work increases more than 9 times. So this is subquadratic method. Next figure is we compare with existing techniques. We can say that all methods also achieve the best practical efficiency. and our method is 10 times better than existing ones. Oh, that's all. Thank you.
So you said those previous algorithms, they are quadratic.
Yeah.
Are you talking about the worst case complexity or the
Worst case.
But then, now, if it's worst case complexity, what is the inherent complexity of the problem? It is quadratic or is?
Yes, quadratic. Yeah.
Because your algorithm only is more efficient, but
Yeah.
it doesn't change the inherent complexity of the problem.
Change the complexity. Sub-quadratic method.
Okay.
It's n squared minus c.
But that's the complexity of your algorithm,
Yeah,
not the complexity of the problem.
Yes,
I was talking about the complexity of the problem. Have you come up with any like a theoretical analysis of the
best
complexity of the
complexity we don't know.
Okay.
It's an open problem, I think.
Okay, I also have a question. So, Surajit have a very well-known paper for such similarity. It's basically the threshold-based
Yeah.
algorithm. And then bottom case sketch in papers such as Peter Haas's paper is about basically for the large sets you take the bottom case sketch and then just use it for a set similarity.
Yeah.
Can I just see your paper as a hybrid method that tries to combine these two methods to each other? And if not, what is the difference?
So we compare with existing work. So all the workers usually using the inverse generate some signatures. But no method, existing method, using the C subset-based method because it's very costly. So we only use this method for small sets. So all existing works using the same method. For example, generate some signatures and using the signature to do pruning. So we compare with them. Yeah. Okay, thank you.